Hi everyone. In this video I wanted to show you how I implemented the PageRank algorithm. If you follow me on LinkedIn, you would have seen that recently I posted this thing here, this article, where they describe how Google's PageRank algorithm, which orders the search pages once you retrieve them, in order to show you the ones that are most relevant and most connected to other web pages. And they described how this algorithm kind of can have an effect on architecture. So if we go to this article, you can read it. I'm not going to go through it right now, but basically they talk about how it can show you how this algorithm can affect the ranking of spaces that are well connected or less than well connected. So it's really interesting, and because it is all based on graphs and based on graph theory, and Topologicpy obviously supports graphs and graph theory, I decided to recreate this example. As you can see here, this is kind of a conceptual floor plan, I guess, of a building with some rooms, and they are numbered from 1 to 10. And the idea is to find out which rooms are the best connected, I guess, and which ones are not. So he applies the PageRank algorithm to it. He doesn't show exactly the code behind it, but basically we can get, oops, sorry about that. That's absolutely fine. Let's go ahead and restart. No, okay. So let's go here and go back to this one. Yep. So let's just go down to here, and then up comes this color coded with the numbers. Basically, the ones with the higher numbers are first in the ranking. So that you can imagine this space is more central in a way, or it's connected to from other well-connected spaces, and some other spaces are perhaps a bit more isolated and less important, like the ones in these corners. So what I was curious about is, does my PageRank implementation in Topologicpy produce the same numbers and the kind of the same ranking? So I went and created a Jupyter notebook based on that, and that Jupyter notebook is available on GitHub. So let me just show you where that is. Let's go to Wasim J Topologicpy. So if you go to my GitHub, which is, sorry about that, let's just find where it is. Yep. So this is the GitHub. Let me show you the URL. It's this one, Wasim J Topologicpy. And in there, if you go to notebooks and scroll down, you will find something called PageRank right here at the bottom. It's called PageRank. You can download it and you can use it. So let's go ahead and look at this notebook and see what it does. So as usual, because I'm on my development machine, the very first two lines you don't need. This is just simply for me to point Python to where Topologicpy exists. And I also should say that this is compatible only with version 0.4.83 or newer than that. So before that, the PageRank algorithm was not implemented. So please download 0.4.83. Okay, so the first step is to import the Topologicpy classes as usual. So I import all of them. I don't probably use all of them, but it's good practice to import all the libraries and classes that are needed. And then this very long set of calls here is basically nothing more than creating the boxes for the rooms, as well as the faces for the doors. So you can see here, these are all the doors. So we have 10 rooms and we have 11 doors in total. And then I show everything so that I am assured that I've modeled it correctly. So this is all manual modeling. Obviously, you could have imported geometry from somewhere else, but if you don't have another geometric editor, basically you can model it from scratch in Topologicpy using these calls. So you can see here, each one of these is a box, separate box, and each one of these faces is a door. And what we're going to do is create a building, a cell complex, and apply these doors as apertures between them. And that's the next step. So as you can see here, I create a building by cells, cell complex by cells, and I give it the full list of the 10 rooms, and it will create for me a single building that has these cells in it. And then I create a list of doors. So these are the 11 doors, again as a list. And then I add the apertures to the building. So I add the doors to the building, and I say I would like to add them to the faces, not to like cells or edges. And they are exclusive. That means every face has only one door. And the result, I store it back in the same variable called building. And then I show the building and the doors. Please know in Topologicpy, if you just show the building, even though it has the doors, though it has the apertures, by default it doesn't show them. You would have to go down to the faces, ask the face to give you its apertures, and then aggregate those and show them. So this is just a shortcut to show the doors along with the building. So here they are. Now this is a full cell complex and it has all the apertures in it. So in order to check our work and to make sure that these are connected correctly through these doors, we are going to create a graph. So we're going to create the basic dual graph to check the accuracy of modeling and topology. So we say graph by topology, and we are saying we don't want direct lines between the rooms, but we would like direct lines only if they have apertures. So direct apertures equals true. So only if they have an aperture between the rooms do we would like to draw a straight edge between them. And then I get the topology of the graph. That means it will be the wire. And then I create the data. This is only because I would like to draw the graph in red with large vertices, different from the building and the doors. So I'm creating a data set for each one. So plotly data by topology, which is different for the graph than for the building, which defaults, and then for a cluster of the doors, which also defaults. And then I create a figure by this data. So you use the plus sign, data 01, data 02, data 03, and then you show that figure. And this is the result. So as you can see, the graph is correct and accurate in the sense that rooms that are connected by doors have an edge between them, and rooms that do not have doors, like 10 and whatever this one, 8 I guess, do not have an edge between them. Like 8 and 7 do not have an edge between them. So so this looks correct now. So we can now proceed to the next step. Now that we have this correct graph, this is, by the way, assumed, and in the example as well, assumed to be an undirected graph, meaning that we will assume that these edges are bidirectional. They go from 1 to 2 as well as from 2 to 1. And that will obviously affect the ranking. So when you calculate PageRank, so you can call graph.pagerank, this is the new method. What does it take? It takes the graph that you have created, the dual graph. You tell it that you do not want it to be a directed graph, or you don't assume this graph to be directed, so it will compute it as a bidirectional graph or bidirectional edges. I did not put the alpha, which is the dampening factor, or damping factor as they call it, which defaults to 0.85 anyway, but you could change that if you would like. But I did also put that maximum iterations here is 100. So just to be complete, we can say alpha equals 0.85. These are the defaults anyway. And we are not asking it to normalize the values. If you set this to true, normalize equals true, it will normalize the values so that the lowest one is 0, like 0.05 will become 0. And the highest one, let's say like 0.13, will become, or 0.17, excuse me, will become a 1. So it will map these values from 0 to 1, if you would like to normalize the values. In this case, just to check against the example that we had, I did not normalize them, and I rounded them to 2 decimal points like he did. and I printed them. And I can tell you that these values are very accurate. They might be 0.01 or 0.02 different from what they had in that article. Okay, so how do we, so we got the numbers, but how do we actually color code the room so that we can see a nice color coded image? So basically, we get the vertices of the graph. We're going to use these as selectors. So we're going to put the dictionary in them and then transfer that to the floors of the rooms. So we're going to have an empty list called selectors, and then we are going to go through the vertices of the graph, which are ordered in the same order as the PageRank list, which is called PageRank here. And we are going to create a dictionary by key value. The key is called PageRank, like this, and the value is PageRank sub I. Okay, so each one of those numbers here is going to get its own dictionary, and we are going to create a new vertex where we are going to get the x and y of the graph vertices, but then the z we're going to set it to 0. And the reason we are setting it to 0 is because we would like it to be internal to the face on the ground level of the room. So the room's obviously starting from 0 up, so the faces are at z equals 0. So in order for the face to recognize that that vertex is internal to it, we are creating a new vertex called S and taking the x and y from the graph but setting its z to 0. And then we set the dictionary of it to D. So now this vertex has that dictionary, and we append it to the list of selectors. And we just simply, just to check, just a reality check here, we're printing the coordinates and the page rank of that coordinate. And you can see them here, just to check. So now what we need to do is get the floors of each room and transfer the dictionaries to them. So we decompose the cell complex. There's a method called cellComplex.decompose. We get the bottom horizontal faces from that dictionary, from that decomposition, and we call it BHF, short for bottom horizontal faces. So this would be a list of faces, and then we create a shell by these faces. Okay, so because they're all sharing edges, we can create a shell. And then we transfer the dictionaries by selectors to the shell. The selectors are the list of selectors that we created earlier on, which are here. As you can see here, all these selectors, all these vertices that have dictionaries in them. And we say we would like to transfer the faces, so the dictionaries that belong to faces. And it will do it automatically. It will match every face with every selector, finds out if it's internal to it, and if so, it will transfer the dictionary to the face itself. Now I'm just going to draw it. So I'm just getting a wireframe of the building and a wireframe of the edges. So this is just for drawing these two things, because I did not want to obscure the faces, because I would like to hover over them and click on them. And you'll see that in the next step. So basically, I'm going to draw the shell, and I'm going to draw these edges. So topology.show will show me the shell and the edges, but I am telling it that I would like for the faces, please, to show the label to be PageRank, which is the key of the dictionary that we used. And also for color coding purposes, the face group key is also PageRank, so please color code by PageRank. And here are the groups that you need to check against. It will check, where that value falls, and it will sort them correctly for you. And I'm using a thermal color scale, to kind of create almost like a heat map. So here is the result. This is the cell complex. These are the edges of the building and the edges of the doors. But then the one at the bottom here, the color coded, this is the shell. And the faces of the shell have this hover label, because I said here face label key equals PageRank. So basically you can hover over it and you say, like, this is 0.1, 0.06, 0.05, 0.13, 0.9, 0.1. This is the most central one, 0.17, etc., etc. And that's it. This, as I said, this notebook is on GitHub. Please download it if you're interested. Go through it. find out what these calls mean and how to run such analysis. I hope you enjoyed this video. See you soon. Bye bye.